Welcome class to chapter 16 on the chi-square. So remember when you were overwhelmed by that big flowchart? Well, this is again a little part of the flowchart, but now you know the whole thing, the whole shebang, right? Which is pretty cool. And in any case, last chapter we reviewed Pearson R tests and regression tests, where you will use those correlational tests when you have a ratio or interval scale. And this chapter you're going to be reviewing, or we're going to be reviewing the chi-square, where you'll be using that correlational test when you have a nominal or ordinal scale. Nominal or ordinal scale. Parametric versus non-parametric tests. Parametric tests are inferential stats tests that can be used to test hypotheses about continuous variables, whereas the non-parametric tests are inferential tests that can be used to test hypotheses about categorical variables, and I gave the example already about nominal and ordinal scales of measurement. And again, if data involve categorical variables, then the non-parametric tests are used. However, they're not as powerful as the parametric tests, so they should only be used when absolutely necessary. Remember, power is defined as the ability to detect a difference in the population when there actually is a difference. So this means that the chance of type 2 error, where you have a false negative, say there is no difference when there actually is a difference, is higher for non-parametric tests. Observed versus expected frequencies. The chi-square test will examine the relationship between categorical variables in terms of what frequencies are expected if there is no relationship between the variables. These expected frequencies are then compared to the frequencies observed in the data collected from the sample. If they differ significantly, then the null hypothesis can be rejected, right? Reject the null hypothesis, it looks ridiculous, and go with the alternative hypothesis. So you're going to collect your data, and that's your observed frequencies. For example, for each class, freshman, sophomore, junior, senior, what are the observed frequency of grades? Okay, so you might hypothesize, for example, that you expect seniors to do really well and get the best grades, and maybe juniors not as well as seniors but better than sophomores, and so on, because they have more experience. Or you might hypothesize that, well, yeah, a good chunk of seniors might get pretty good grades, but some of them might just get C's just because they need that minimum C and they got senioritis or something like that. I don't know, you might have multiple hypotheses to try and figure out kind of, who does what, and if the grades differ by class. So you're going to collect your data, and you'll take a look at those observed frequencies. And then you'll also calculate your expected frequencies so you can compare the data and kind of see if your correlations of your hypotheses are true about your seniors, and if they do better, for example. Based on what you observe, and you calculate your expected frequencies, again, based on what you would observe if no relationship, for example, or that is, for each class, we expect all classes to equally perform. There's an equal distribution of A through F grades in the class. So you are calculated, our expected frequencies are based on what you would observe if there's no relationship. Okay, so you would think that regardless if it's freshman or senior or anywhere in between, they're all going to get an equal distribution of A grades, for example. Okay? And again, mise en place, right? Just figure out the formulas, have your materials there, or your numbers that you need to plug in, then just plug in and then do your PEMDAS. Make sure you do the orders of operation correctly. And easy cheesy, right? Lemon squeezy, as my daughter says. So this kind of gives you a little bit of the, little piece of the expected data and the observed data. And so what we need to do is, again, mise en place, right? We need to take a look at our expected frequencies, and we want to figure out those first before we start doing the calculations. So the formula for the expected frequency is the column totals times the row totals over the total of students, for example, or participants in your population. Okay? So take a look at down here. So you have 30 A grades. Okay? So you have A, and there's 30, and this is your observed totals here. So you actually observed that out of 200, 30 students earned A's, okay? Now, if everyone in the population was the same, freshman, sophomore, junior, and senior, they would all be 50, 50, 50, 50, and that would equal 200. And then down here, the expected frequency would be just 25% of 30. Well, half of 30 is 15, and half of 15 is 7.5. So 25% of 30 is 7.5. Because these are 25%. And if these were 50 and 50 here, the juniors and seniors, it would be the same. 7.5, 7.5, 7.5, and 7.5. But the expected frequencies are not there because we have to, for juniors and seniors, are not 7.5, because we have to adjust the fact that juniors have 60 versus 50 people and seniors have 40. And so that's why we take the ratio of the total number of students, for example, 50 students, times the or over the total number of freshman students, 50, over the total number of students, so we can get the proportion, and that's of course 25%, right? So then we will multiply 25 times 30, and that gives us 7.5. But again, the ratio, I'm just kind of explaining why you have this formula right here, because it will give you the expected frequencies according to how many people are in the population. Okay, hope you can see that. In any case, so you take the column total right here, and for freshmen, it's 50 freshmen, and 50 right there in the column F subcolumn. And then you take the row total, which is 30, so you multiply 50 times 30, and over 200, and that gives you 7.5. And you do that for each one. So each one for the A, for example. And then you do that for the B's and so on. So hopefully that explains the calculating expected frequencies. And this is the data in sum. And so this is what we're going to be comparing. And at the end, when you get your chi-square statistic, you can kind of, it just tells you if there's a relationship or if there's some type of relationship and if it's significant or not. It doesn't tell you where, so you can compare these things right here. And as you can see from observed, let's just check out A's, because, you know, hey, A is pretty cool, right? And let's check out the seniors. So the seniors observed, they earned 11 A's, but we only expected them to earn 6 A's. So it looks like the seniors, boom, did pretty well, right? And for juniors, about the same in terms of what we observed versus what we expected. Sophomores, about the same. And freshmen obviously didn't perform and didn't do super well compared to what we expected if there was an equal distribution. Okay, so that gives you an idea of how you compare the observed grades versus the expected grades. Okay, and if there's a significant difference, you might say, oh, well, that makes our data look, you know, ridiculous, that there's no relationship. Seems to be there is a relationship between grades and class and letter grades, right? And then you can conclude that. So we'll see. It looks like that might be a pretty powerful thing. But remember, our chi-square is not picking up power. So if we could translate these grades into numbers, which grades are numbers, right? Okay. Then we might be able to pick up a difference. And you'll see later in the example where they gave, I think, the age and whether or not you remember to turn something in. That in the previous example, in the last chapter, when they talked about the Pearson R, it was significant. But in the chi-square, as you'll see, it's not significant. So not as powerful. In any case, calculating a chi-square by hand, you're like, yeah, why do that, right, when I have SPSS? But nonetheless, let's take a look at it, and you can kind of get the ins and outs and the feel for it, right? Step one, remember the hypothesis testing procedure is the same. You're just using a different statistic, different appendix, right, to look up your alpha value and your critical value. But anyway, I digress for a little bit. Class standing and final grade example. The null hypothesis in the population of students, there is no relationship between class standing and the letter grade in the course. And the alternative hypothesis in the population of students, there is a relationship between class standing and their letter grade in the course. Step 2 is to set decision criteria, 0.05. Like the F distribution, the chi-square distribution cannot be negative. Therefore, there's only a tail of extreme values on the positive end of the distribution. As with the F statistic, the shape of the distribution depends on the degrees of freedom, and we'll use that when we look up in our appendix our F crit, or our critical value for, not F critical, our critical value for R, or R squared, the chi-square. And again, so we're going to collect the data, the sample data, and here's the observed and expected, just a reiteration of that slide before, a couple slides back. And then I'm going to kind of go back and forth between this data right here and then this formula, just to show you where I plug in this information. Because remember, it's mise en place, right? So you would ideally have this data right in front of you, and then another screen or another piece of paper where you have your formula, and then start plugging it in, okay? So the formula for chi-square is the sum of the observed minus the expected values squared over the expected values. So let's take a look at how we're going to plug those in. So you can see right here, freshman A, 3, and that's the observed, and then the expected is 7.5. So we're going to subtract that, and you have 3 minus 7.5. We're going to square it, right? And it's over 7.5, which is the expected. Remember, these two values will be the same. It's the expected, right, value there. So where's the 21 and 17.5? Let's go back. And you have that right there, B's for freshmen. So we're going to go through the freshmen in this equation on the next page that I've been kind of shifting back and forth. We're going to go through the freshman instances of observed minus expected, observed 21 minus 17.5, and that's what you have right here, plus 21 minus 17.5 squared over 17.5. 12 minus 17.5, yeah, you guessed it, that's the C grade. 12 minus, it looks like it's 15 there. Oh, yeah, 12 minus 15 squared, so the book's not wrong. Woo-hoo. And then 8 minus 6.25, that's the D. And then 6 minus 3.75, notice the, again, observed versus expected. So you really plug in all of those values right there. I did the freshmen. This is the sophomore, juniors, and seniors. Add them all up using your PEMDAS, right? Parentheses, exponents, multiplication, division, addition, and subtraction. And then you get 23.03, which is your chi-square value. Chi-square value, 23.03 right here, and you have the degrees of freedom. And how do you figure out the degrees of freedom? Well, you take the number of columns and subtract it by 1, and multiply it by the number of rows and subtract it by 1. So let's take a look at the number of columns here. 1, 2, 3, 4. So we have 4 minus 1. Let's take a look at the number of rows. 1, 2, 3, 4, 5. And you have 5 minus 1. That gets you to 3 times 4, and that's 12. So our degrees of freedom is 12, and our chi-square value is 23.03. What we will do is look up that value to find our critical value, our chi-square critical value. And so in order to find the critical value of chi-square for the degree of freedom with 12 and alpha level at 0.05, you need to look up in Appendix F this time. It's pretty simple when you look it up, so I didn't actually put the appendix up here. You'll quickly see that at 0.05, the critical value is 21.03, and our chi-square value is 23.03. So did we meet it and get into the critical region? Remember, we're trying to plug away and go past the critical region into that far region right there, and the answer is, of course, yes. This means that our calculated chi-square value is in the critical region, and thus we can reject the null hypothesis It looks ridiculous that there's no difference in grades. And as we suspected when we looked at the differences, let me go back right here, it's seemingly a difference in grades, right? It seemed like the seniors were doing a little better than the freshmen, for example. The last part, in terms of the SPSS output, this is not the same study as the grades and class. It's the study of whether or not older people versus younger people remember to turn in a postcard, and if they're on time. And if they turn it in on time, they got yes, and if they didn't turn it on time, they got no. And it looks like the older people turned it in on time much more than the younger people. And the chi-square output for SPSS shows you that right here. And you'll recall in the Pearson R, this same study with the same data, that it was significant. But if we look at our chi-square here, the chi-square is 3.33 and shows you your degrees of freedom. And then it shows it at 0.068, which is not below 0.05. So as you can see here, when you run the chi-square, you're not able to pick up the differences when there actually are a difference that you picked up in the Pearson R. And that is it. I hope you enjoyed the lectures, and keep up the hard work, class, and take it easy.